The minimum and maximum comes up in a reliability analysis, worst case, best case, right? Analysis. So more generally, if you have, so we'll, in fact, a little later I'll look at this problem. Minimum of a chain of random variables. I think I went through this, right? Suppose the xi's are the lifetime of a component, let's say electric bulb or something. So minimum represent, the question is what is the average lifetime? To find the average, of course, average lifetime is going to be summation of xi, I equal to 1 through n. So, of course, you can find the average and say the average is 5,000 hours or whatever. But the issue with this is you have to wait till if there are 10,000 lights here, you have to wait through all the 10,000 lights blow up, and that may take years and years. Whereas if you do this, so this is another parameter. You can, let me say the minimum. Minimum is easy. As soon as you switch on 10,000 lights in a room, and instant the first light goes away, you have the minimum. So that's so in quality control, etc., using the minimum, especially if things need to be done, it's another. So this is a feature about all these lights, light bulbs. This is also a feature. So this is what we have studied so far, right? x1 plus x2 plus etc. x, sum of random variables divided by a constant. Constant is not going to change the nature of the random variable. That's another, except this is a linear function, that's a non-linear function. So let's find the density function of z. So I'll start with the distribution function. Z is less than or equal to z. So z is given to be minimum of x comma y less than or equal to z. So it's not easy to separate out the minimum, except if you consider this is a natural partition to consider these cases, because here, because if x is greater than y, what happens to the minimum? Anybody? It's just y. And if x is less than y, x. So we should be able to, so that becomes linear. So the question is, how do we bring in that one? So again, you see that S can be written as A union A complement, where this is A. So this is A complement. And so if I write this to be some event B, I can write this as B union, B intersection S, but S is A union A complement. So it's the same argument as before. So this is P BA union BA complement. A and A complement are exclusive. So this is PBA plus PBA. Why am I writing all this? Look at how this simplifies now. So this reads now probability of A is what? A is a minimum of x comma y less than or equal to z, and x greater than or equal to y plus probability of minimum of x comma y less than or equal to z and x less than y. But look here, in this x is greater than y, this is just y. So I hope you see this. This is probability of y less than or equal to z, x greater than y, plus probability of x less than or equal to z, x less than y. So let's draw a region where these regions are. So where is this region, x greater than y? Anybody? So this is x equal to y. Where is x greater than y? To the right. And where is this region, y less than z? So I hope you see this is the region x greater than y. And if y equal to z is here, so let's say this is z comma z, then so this is the line This is the line y equal to z, right? Below that, but under this, so it will be this region, right? So let's come here. By x less than y, it's on to the left side, and x less than z. So x equal to z is here. This is x equal to z. So it's this region. So if you put it together, I hope do you see this? This is the region you should be integrating. Yes? Because this point is the same as this point. Yes? See this region and this region together. 1 and 2. So if you want, you can also say that this region is the same as 1 minus this region. What is the property of this region? Anybody? This is the region x greater than c and y greater than c, if you want. So many ways you can express it. And remember, this of course you can write this as, how do you express this region? This is which region? This is y less than z. This is x less than z. But I included this region twice, so you take it out. So I hope, do you see this? So this is probability of x less than z plus probability of y less than z minus probability of x less than z, y less than z. So that's fx of z plus fy of z minus fxy c comma z. So that's the distribution function of z. So let me do this for x and y are exponential. X is exponential with parameter lambda. Y is also exponential with parameter lambda. X and y independent. So look at this, I am solving this problem. This is, I copied this line here, except I made use of the independence here. If it is independent, the distribution function will be the product, right, here. So now to find the density function, I take the derivative with respect to z. So what's the derivative of this function with respect to z? Lowercase f, right? Derivative of this, big capital F is small f. How do you find the derivative of this with respect to c? Huh? Then? Chain rule, right? Alright, so let's substitute. So fx of x is 1 over lambda e raised to minus x over lambda. So we need the distribution function. Anybody? What is fx of? Anybody remembers how to compute the distribution function? So if you want, you can write this as 1 minus fx of z multiplied by fx of z. I combine this these two terms plus 1 minus fx of z all right. Fx of z is what? The area of z less, so 0 to z, the density function. I changed the variable to u, so this one. Let's evaluate this. So this is e raised to minus u over lambda over minus 1 over lambda 1 over lambda here, 0 to z. So that's 1 minus lambda, lambda cancels. So 1 minus e raised to minus x over lambda, right? So 1 minus fx of z, I mean fx of x, fx of z, that's right. So this will be z. 1 minus fx of z will be e raised to minus z over lambda. So let me substitute it here. So this is e raised to minus z over lambda. This is 1 over lambda e raised to minus z over lambda. And this is exactly the same thing. So this is 2 times that. So you get 2 over lambda e to the power minus, what do you get? So what's the density function of this? This looks like? We started with the exponential, what do you get? So that's a theorem. If x and y are independent exponentials, the minimum is also exponential. With parameter lambda over 2, so 2 lambda, whichever way you want to write. So another way to do minimum, let me show you this also. You may not want to go through all the graphs. So let's take this more general problem. Z is minimum of x1, x2, etc. Let's solve this problem. So FCZ is probability of z less than or equal to z. But this is the same as 1 minus probability of z greater than z. That's certainly true because this has to be 1. So this is 1 minus probability of a minimum of x1, x2, etc. All right, now here comes the part whether you like it or not. If minimum is greater than z, what can you say about each one of them?
Greater than z.
So I hope is this one and the same? This is the big part here. So I avoided all this last time. So this is true. I mean, I'm going to assume here also xi are independent. So look here. So this is the same as saying 1 minus probability of x1 is greater than z, x2 is greater than z, etc. etc. Because if minimum is greater than z, each of them has to be greater than z. And if that is the case, now we can use the independence. If they are all independent, that becomes 1 minus product of I equal to 1 through n, probability that xi is greater than z. Right? But that's the same as product of I equal to 1 through n, 1 minus probability of xi less than or equal to z, right? Because probability of xi greater than z is the same as, so that's the same as 1 minus product I equal to 1 through n, 1 minus fx. But 1 minus fxi is here, look at here. 1 minus fxc is just this for exponential. So if they are all exponential, then this is just e raised to minus z over lambda. n times. So this is 1 minus e raised to minus nc over lambda. That's the distribution function. So let's take the derivative with respect to z. So you get fzz. What's the derivative? Look, this is also exponential, so you get another result. So if you have exponential random variables which are independent, then the minimum is also exponential. So let me do the maximum, then we'll stop. Any questions here? Or maybe we'll do minimum over maximum, one more. So again, you can draw the graph, etc. But maximum we can also do it. So w is max of x comma y. So fw. So we can also do a quick argument. This is w less than or equal to small w. But w is given to be max of x comma y less than or equal to. So again the same argument. If maximum of two quantities is less than c, each one of them must be less than or equal to c. So that's the same as saying x must be less than or equal to z, y must be less than. This is true even if you have x1, x2, xe, etc., etc. But this is nothing but fx, y, z comma c. So this is a little easier. Of course, at this stage, if x and y are independent, then fww would be and in that case fww, the derivative will be the derivative with not z, this is lowercase w. So derivative of this, which will be fxw multiplied by capital Fyw plus fxw etc. So before I finish, let me do a so let's say x is let's do that problem what for maximum. Let's say xi's are uniform from 0 to a, and z is maximum of x1. So it's exactly the same as what we just did, except a maximum. I mean, so we can just extend this argument. So look here, it goes like this. All of them are identical. So fzz is probability of z less than or equal to z. But z is given to be maximum of x1, x2, etc., xn. That means each one of them is less than or equal to z. But they are all independent. So that becomes the product I equal to 1 through n, probability of xi less than or equal to z. But this is just the distribution function product. A capital F of xi z. But for uniform, fx of z is integral 0 to z, the density function of x dx. So 0 to z, 1 over a dx. So this is just a z over a, right? So this is z over zn over an, and z goes from 0 to a. So you should be able to do problems of this type. So the density function of that is just the derivative of that, right? So here comes a problem. If you want a practical problem, let xi's represent. So you want to construct a dam, and so there is water here. So let x1, x2, etc. represent the water level over the last 100 n years. Xi is the rainfall, right? So this is a random variable, right? You don't know. So you can look at the data and see for the last 100 years what was the rainfall here. How high was the level? So maybe somebody has noted. And if you assume that rainfall is, between, so you take the worst case and say the rainfall is uniform in that 0 to whatever, let's say 20 feet or something, or 30 feet. So now you know the, so the question is how high should be the dam? So what is one sensible criterion? The dam should be higher than the worst case, right? So you could say probability of the dam. So this is one way to, because we don't know h. So we could say the probability that the height exceeds the maximum, or the other way maybe makes more sense. In the worst case, the maximum, you don't want the new flood to exceed the dam height, right? So this exceeding the dam height must be less than some, whatever you want to conclude here, 10 to the power minus 4 or something. So we already know the density function of this random variable. So that's just this is what? This is 1 minus the distribution function. If you call the maximum to be z, this should be less than 10 to the power 4. So you can solve for h. What it says is if you construct a dam here, we don't want the water to, the dam to stop the water. That's the whole idea of the, we don't want this to overflow. So the probability that this will overflow should be less than whatever you want to put. So finally, let me do one more problem, or the ratio of two random variables. I guess there are, we can do it next time, or I'll just maybe describe the problem.